Now, the next thing I want to do is to talk about bond energies for all kinds of covalent bonds, polar and otherwise, and how they can be used as the fourth method that I'm offering you this semester for calculating delta H of reaction. Remember, we said there were three others. One was actually this is the determination. You could do it calorimetrically, or you could do it with the first kind of Hess's law, the second kind of Hess's law, and this is the third and last way that we can use to get this stuff. Okay? And so here's an enthalpy diagram to get us started. And we have a reaction here between two homonuclear diatomic reactants, and they combine in this sequence to give two, if this is X2 and Y2, to give 2XY. Okay, to give the diatomic molecules where the atoms are different. And of course, the delta H for this reaction is the difference between the enthalpy of the reactants and the enthalpy of the products, as we've seen before. Now, Hess's principles can be used to figure out a way to get this number without carrying out the calorimetry or some other route. For gas phase reaction, and this only works in the gas phase, the bond energies of the reactants can be thought of as having to be overcome to make atoms, and the delta H, the first delta H term would be the sum of the bond energies for all the reactants, and that would make, we would break X2 and make two X's, and we would break Y2 and make two Y atoms. And the second thing would be, this plus sign here is because breaking bonds cost money, costs energy. Okay, so that's endothermic. The second thing, we let the atoms come together and form new bonds, that's exothermic, so there's a negative sign there. So delta H reactions equal to delta H1 plus delta H2. The length of this arrow and the length of that arrow have opposite signs. Okay, so the idea is we will use bond energies for gas phase reactions to get an estimate of what delta H reaction is, particularly for reactions where we can't measure. All right, let's suppose we go back to the light cannon. Remember back in chapter 6, I showed you the cannon that if you put H2 and Cl2 into it and then shone a bright light on it, the cannon would fire and shoot the cork out. And we talked about why it fired, all this sort of thing. So we'll go back to that and see if we can determine how much enthalpy change actually occurred using this method. This is a gas phase reaction, so that's good. That should be appropriate for what we want to talk about. So in looking at this, if this is H2 and this is Cl2, then this will be HCl, and this will be HCl. And the delta H for this process can first be expressed as the delta H of reaction is equal to the summation of delta H bonds broken. Okay? These are the bond energies. Plus delta H of bonds formed. And this is endothermic. This term is endothermic. That's this one up here. And this one is exothermic. So we'll do our calculation. We'll look at the bond energies and see what the results suggest. Okay, let me turn that off. The bond energy values for H2 is 432 kilojoules per mole. For dichlorine is 243 kilojoules per mole. Everybody see that okay? Then for HCl, it's 427 kilojoules per mole. So now we have everything we need to do the calculation, and you'll get to do some of these in the homework for this chapter and very likely in other places as well. So the delta H reaction, according to this method, is the bond energy of H2 plus the bond energy of Cl2 minus 2 times the bond energy of HCl. There's 1 mole of H2, 1 mole of Cl2, and 2 moles of HCl. So we have to put in the number of moles. The bond energies are in kilojoules per mole, and we'll multiply that by the number of moles in order to get kilojoules, because delta H reaction is not, I repeat, not in kilojoules per mole. It's kilojoules. Okay, we plug in the numbers. 1 mole of H2 times 432 kilojoules per mole, plus 1 mole of Cl2 is 243 kilojoules per mole, minus 2 moles of HCl at 427. And this is almost 180 kilojoules per mole. Certainly enough to pop the cork out of the cannon. Questions on this process? If you, for example, have a problem that asks you to calculate a delta H and they don't give you any information, and it's a gas phase problem, this is the method that you use. Okay? If they give you bond energies, it's pretty clear what they want you to do. But if they give you nothing, then go back to table 9.2 and get your bond energies there and plug them into this equation. So what do you need to do? You need to determine the reactants and the products and the balanced chemical equation. Then you do the delta H reaction is equal to summation of the bonds in the reactants plus the summation of the bonds in the products, all of them. All of them. Okay, questions on that? I'm going to do a more complicated example because I find that it's very easy to make an error in these things. So I want to just go step by step through a more complicated one. And this is going to be the chlorination of methane to form chloroform. Nice organic chemistry one. Okay? So methane is CH4. The first piece of advice that I need to give you, and you need to take it, is when you encounter one of these problems and you've got the balanced chemical equation, write the Lewis dot structures for every reactant and every product, because only from that can you tell how many bonds of each kind there are, because maybe they'll be not just all single bonds like we've seen here, but they might be double bonds or triple bonds. If you don't draw the Lewis dot diagram, you won't know, and some devious professor probably will put in an answer in the multiple choice that corresponds to you just going ahead without checking. Don't let it happen to you. Okay, so methane is CH4, chlorine is Cl2, and CH4 gas plus 3 Cl2 gas goes to CHCl3 plus 3 HCl. And these are all in the gas phase. So that's the balanced chemical equation, and this is the balanced chemical equation written in the way that you need to write it in order to use this method. So we have 4 CH bonds per mole here, 4 moles of CH bonds per mole. We have 3 chlorine-chlorine bonds. In chloroform, we have 1 CH and 3 CCLs, 1 CH and 3 CCLs. And of course, in 3 HCLs, we have 3 hydrogen to chlorine single bonds. And the latter are the bonds that are formed, and the former are the bonds that are broken. When you get one this complicated, it helps if you write a table of the summation of the bond values. What I would suggest is you go through first and write from chapter 9, table 9.2, write the CH bond energies, for example, here. And write the CL bond energies. And then each one of the bond energies here, the CH and the CCl, write them down. Okay, and over here, the HCl bond energies. And then make a table. And here is the table for the reactants whose bonds are going to be broken. It's 413 kilojoules per mole, which is what should have gone in right here. And there are 4 such bonds. This is one CH bond, and there are 4 of them in the molecule. So 4 moles of CH bonds times 413 kilojoules per mole is 1,652 kilojoules. Likewise, for 3 chlorine-chlorine bonds, it's 3 moles times 243 kilojoules per mole. That's 749. And the summation of the bonds broken is this number, 2381. Okay. In the case of the bonds formed, we have 3 CCl bonds, 1 CH bond, and 3 HCl bonds. Now, every once in a while, I run into a tutor in the tutor room who advises, well, you got 4 CHs here and 1 over here. Why don't you cross this out and make this 3? It's the quickest way to make an error you're ever going to meet. Just write it out all the way. You can do the arithmetic. You can, I assure you. Don't bother canceling things. Okay? Just write it all out the way it's supposed to be, and you'll be much safer. We got a lot of noise coming from over here somewhere besides the toilet flushing. Do we have a question? I'm sorry, I couldn't see who was talking. If you have a question, I'll be glad to help you. And I'll close this door in case it's somebody outside, making me think one of my students would be talking. Okay, sorry. So we're ready to finish this up. The delta H reaction, again, is the summation of the delta H for the bonds broken plus the delta H of the bonds formed. And that's 2381 plus a negative 2711. And that's the summation of the thing is negative 330 kilojoules. So this reaction gives off 330 kilojoules per mole of methane. That such calculations of delta H reaction depend on the difference in the bond energies of the reactants and the products. In fact, what we have said earlier was that the delta H reaction for a gas phase reaction is equal to the summation of the bond energy of reactants plus the summation of the bond energy of the products. And the product bonds are formed, so this is really a negative sign in front of any bonds that are formed and a positive sign in front of any bonds that are broken. Energy in to break the bond, energy out when you form the bond. Now, what we need to know is what bonds there are. And we have learned now how to draw the Lewis dot structures for molecules. So the next thing I will do is redraw the equation using Lewis dot structures. And that's exactly what you should do when you encounter these problems. First of all, N2, we noticed N2 was a molecule, a diatomic molecule with a triple bond. And N2 then in the gas phase reacts with dihydrogen in the gas phase. Of course, dihydrogen is easy to write. And those two form 2 ammonias. So I'm going to write the 2 out here, 2 moles of ammonia, And then I'm going to write the Lewis dot structure of ammonia like this. So that I can see what bonds will be formed in getting these products lined up properly here. So the delta H reaction is equal to the number of moles of each bond times the bond energy for that bond. So the delta H reaction, to start with, is equal to 1 mole of N2 times the bond energy of N2, a triple bond, nitrogen-nitrogen triple bond, plus 3 moles times the bond energy of HH, single bond, and then minus 2 times 3 bonds, 2 times 3 moles of NH bond, times the bond energy of the NH bond. Questions up to here? Okay, then it's plug and chug after that. It's 1 mole here times the bond energy of triple bond N2 is 945 kilojoules per mole. So the moles will cancel and we'll get out in kilojoules in that part. Then we got 3 moles times the HH bond energy. That looks like 432 per mole. And then minus 2 times 3 is 6 mole of NH bonds, each of which is worth 391 kilojoules per mole. And you can see in each one of these terms the moles are going to cancel. Our answer will be in kilojoules. The numbers I got, 945 kilojoules plus 1,296 kilojoules. You can check yourself if you're willing to do so. Minus 2,346 kilojoules. And that boiled down to negative 105 kilojoules for delta H reaction.